Good afternoon, everyone. Firstly, I would like to take this chance to thank the conference chairs, Professor Tao Xiaoming, Professor Yan Wei, and Professor Zhen Zijian for putting together this wonderful conference and for the very kind invitation. I really appreciate this opportunity to introduce the research of my group. Today, I'm going to talk about the recent progress of my group in soft network materials and their applications in biointegrated devices. During the last few years, the research of my group focuses on development of 3D microelectronics with customized mechanical properties. These electronic devices include 3 core elements, including complex 3D geometries, customized mechanical properties, as well as functional integration of sensing, actuation, and information processing elements. These 3D microelectronic devices can provide an ideal interface for seamless integration of physical devices and biological tissues and organs. They also provide an important platform for development of 3D functional biomimetic systems. Therefore, relevant research in this direction has very important applications in healthcare, tissue engineering, and other fields. There are 2 grand challenges in this research area. First, soft biological tissues usually show very strong nonlinear mechanical responses. For example, the J-shaped stress strain curves, as shown here, are very difficult to accurately reproduced by chemical synthesis of soft materials. Here, the difficulties include how to reproduce accurately the complex and even irregular microstructures of soft tissues. Therefore, one of the technological challenges we face here is how to develop soft architectural materials and electronics with customized mechanical properties. In particular, how can we develop material designs that can leverage microarchitectures with traditional engineering materials so as to achieve mechanical properties that can mimic those of soft tissues? It's noteworthy that by using conventional engineering materials, the integration of electronic components could be highly simplified and quite straightforward. If you want to further add some complex functions to the 3D microstructures, an urgent need is to build microelectronics with desired 3D shapes. Because the plano microelectronic technologies have already approached their physical limits, we can note an evident lag here in recent years between the development of integrated electronics and the prediction of Moore's law. So here you can see a clear gap here. Since the 3rd dimension can bring brand new opportunities, the 3D micro and nano electronic devices have become a very important research direction in the era of post-Moore's law. But here, a grand challenge is how to develop manufacture approaches that can enable the formation of complex 3D mesostructures in inorganic semiconductors, such as the single crystal silicon, the most important material in the current information industries. To address these challenges, my group has been engaged in the development of flexible mesostructure technologies through uses of mechanics principles and highly interdisciplinary studies. And based on these technologies, we developed unusual soft network materials that can reproduce the mechanical properties of soft tissues. We also developed a mechanics-guided assembly approach that can form flexible electronics with customized 3D shapes. Today, I will focus on this part and highlight our network designs so as to achieve customized mechanical properties. In particular, we have established a class of soft network designs and manufacture approaches. The key idea is to incorporate strategically designed microstructures into the lattice network and to utilize the composition design and the geometric optimization of the microstructure so as to tune the effective mechanical properties of the entire network material. On one hand, we have developed design strategies to achieve a range of biomimetic properties and unusual properties. The examples of those mechanical properties include the biomimetic J-shaped stress strain curves and the imperfection-insensitive properties, as well as the unusual modes of swelling, thermal expansion, and Poisson's ratios. On the other hand, it's also crucial to develop quantitative mechanics models that can serve as the design basis and to dictate the structure property relationship. Additionally, we are also interested in exploring unique applications enabled by these network materials. Firstly, please allow me to show you the Bioinspired network designs. As you can see from the two images on the left and the right top image, the collagen fibers is usually composed of irregularly distributed helical structures that are connected at certain joints. So when these helical collagen fibers are under uniaxial stretching, for example, you stretch it uniaxially, these helical collagen fibers unfurl, straighten, and stretch in a manner that gives a low modulus at small strains, but with a sharp transition into a high modulus regime at large strains. So the result is a J-shaped stress strain curves, as you can see here. And this is attributed to the deformation mechanism of bending-dominated and twisting-dominated deformation into stretching-dominated mode at large strains. So inspired by this deformation mechanism in helical collagen fibers, we propose a biomimetic deterministic design as illustrated on this slide. The key idea is to develop an engineered artificial polymer in which the helical microstructures, inspired by the collagen fiber, serve as the building block, and the periodical lattice pattern form a regularized network. And in this design, different 3D topologies can be exploited to form the 3D network material. And here are three representative examples, including the cubic network, the octahedral network, and the octet network. The images on the top, as you can see here, correspond to the design cartoons, and the images on the bottom shows the optical images of 3D printed samples. So here with the commercial PolyJet 3D printer, we can achieve a robust production of 3D network materials with a fiber diameter down to 100 microns. And this video shows the fabricated 3D network materials can undergo large levels of stretching, compression, bending, and twisting deformations. And based on our mechanics modeling and design, we can ensure that these microstructures only undergo elastic deformation. So these deformations are elastic and reversible during these loadings. To analyze the nonlinear stress strain curves of the 3D network materials, we have developed computational models with use of periodical boundary conditions. And such models can save a considerable computational cost, but does not reduce the accuracy of the prediction. As you can see here in these curves, the finite element calculations with these periodical boundary conditions agree well with the full-scale finite element analysis and the experimental results. And the deformation images are also in good agreement with the optical images in experiments. To facilitate the nonlinear, the network design, we have also developed a micromechanics model that can predict the J-shaped stress strain curves of network materials with a variety of geometric parameters. The quantitative mechanics modeling also allows a clear understanding of the structure property relationship of the network materials. And based on this theoretical model, we can easily perform inverse design of the network material to reproduce the J-shaped stress strain curves of biological tissues. So here are two examples. On the left top image, the black curve is the stress strain curve of a human heart muscle. And the blue dots correspond to the results of the artificial 3D printed material, which agrees fairly well with the J-shaped stress strain curves of real heart muscle. On the bottom shows another example for the right ventricular myocardium of an adult rat. And here the stress strain responses are very different between the circumferential and the longitudinal direction of the tissue. And for such anisotropic mechanical responses, the artificial tissues based on our network design can still reproduce accurately the stress strain curves of biological tissues along both directions. By degenerating the 3D helical microstructures into 2D, we can create planar network materials consisting of horseshoe microstructures. And this kind of 2D network material can be tailored to reproduce mechanical properties of film-shaped tissues, such as animal skins. This kind of 2D network material can be fabricated much more easily than the 3D networks. And excluding the 3D printing, the photolithography and the laser cutting technologies can be also exploited. And either the polymers and the metals and the semiconductors can be used. So here, the images shown in the left illustrate the fabricated network materials wrapped onto the tip of the thumb. Actually, human skins have different J-shaped stress strain curves for the skins at different locations of people with different ages. For example, if you compare your skin at the abdominal region with your skin at your back, you can see that they show very different mechanical responses. And you will find that the skin at the abdominal region is much softer if you stretch it, and it leaves a much higher strain before it's hardening. So this is also evidenced by the experimental results of the real skin as shown in the right of this slide. So here, the back 1 and back 2 correspond to two different locations at the back region. And here, based on the micromechanics models we published in JMPS in 2016, artificial skins can be designed to precisely reproduce the stress strain curves of human skins at different locations. Okay, the developed soft network materials also show a Bioinspired imperfection-insensitive behavior even when the network is made of brittle materials. We know that when there is a circular hole in a solid brittle material, there will be a strong stress concentration around the hole. And this will result in a large reduction of the strength under uniaxial stretching, typically around 60% of the original strength for ideally brittle material. And the stretchability is also reduced significantly. So here, even when we use the brittle material to construct this soft network, the strength and stretchability can be quite imperfection insensitive. So we have studied a range of different circular holes in the network, including different sizes and different positions of the holes. And here is a representative result. And here the blue color denotes the stress strain curve of a perfect network material. And the red color denotes the imperfect network with 6 missing microstructures. And in this case, you can see that the strength reduces only by around 20%, and the stretchability reduces only by around 10%. So this clearly shows the imperfection-insensitive behavior. Okay, this kind of soft network material can be designed in a stacked multi-layer configuration so as to serve as a general platform for incorporating individual components and the interconnects. And this kind of cellular network encapsulation does not pose any essential constraint to the buccal deformations of the interconnect. And therefore, it can enable a substantially enhanced elastic stretchability of the serpentine interconnect as compared to the traditional PDMS encapsulation. Okay, we can see this video again. From this comparison, you can see that the interconnect can deform almost freely in this case to unravel while buccal deformations. But in the case of PDMS encapsulation, the deformations are constrained by the solid material. As a result, the stretchability of the cellular encapsulation can reach around 8.5 times that of the traditional PDMS encapsulation. Okay, the stacked configuration also significantly increases the function density of the system and decreases the literal size of the entire system. In this case, so in this example, the function density is 100% and 110%, and the system is only around 11 millimeter by 10 millimeter, which is much smaller than the previously reported systems with a similar level of functional complexity. So from this comparison, you can also see that most of the previously reported stretchable systems have a function density of only around 50%, and our system has a function density of 110%. So the resulting device system can be mounted comfortably on the skin to serve as a compass display or a sensory mouse. So this video shows a function like the mouse. So you can record the trajectory of your hand and display it in real time on the computer. And this video shows the function to control the movement of this box. Great. Excluding the biomimetic properties, we also want to explore some unusual properties that do not exist in natural material, such as the mechanical metamaterials. One of the properties we studied here is the unusual mode of swirling, such as the large lective swirling. And this requires the material to shrink largely during water absorption. And here the key idea is to incorporate a heterogeneously integrated microstructure into the lattice network. And this video shows the construction of this composite network. In particular, we want to devise a filamentary microstructure that shrinks during water absorption. And this drives us to look into this sandwiched microstructure with a passive layer to serve as a support and a very thin encapsulation layer to ensure a good interface between the hydrogel and the polymer support. And this kind of sandwich design can easily transform the swirling of hydrogel into bending deformations. And as a result, it can lead to a reduction in the end-to-end distance. And therefore, by using this as a building block, the area of the entire network can be reduced largely after water absorption. And this kind of composite network can be fabricated using the multi-material 3D printing. Okay, this slide shows the simulated deformation process during the water absorption and the dehydration process. And the deformed configuration agree very well with the optical images in experiments. If you calculate the value of linear strain, you will see this design can achieve a lective swirling ratio up to around 50%. And this corresponds to around 70% area reduction of the entire network, which is unachievable previously. Additionally, the network also almost recovers to the initial state after dehydration, indicating a very good reversibility of the deformation. Okay, based on this network design, we can easily achieve anisotropic swirling behavior by using heterogeneous microstructures in the network. For example, by putting hydrogel only along the diagonal direction, okay, you can achieve a unidirectional shrinkage only along the x direction. So there is a almost no expansion or shrinkage along y direction. If we describe this swirling path in the space of string components, epsilon x and epsilon y, then we can do a comparison between the current metamaterial design and the traditional engineering materials, as well as previous metamaterial design. Actually, most engineering materials show very small swirling ratios, typically in this region. The well-synthesized hydrogels can offer linear strain beyond 200%, but typically in an isotropic manner. Professor Katia-Bortoldi's group at Harvard developed an architecture material that can achieve around 20% isotropic negative swirling. So there are still many blank areas in the strain space. The network design proposed here can fill those blank areas inaccessible to the traditional active materials. So this kind of design concept can be extended further to achieve unusual modes of thermal expansion. So here you need to introduce two materials with a relatively large difference in the coefficient of thermal expansion. So here we can use PI and PMMA, two kind of polymer material to serve as a constituent material of the network. So here is an example that offers a unidirectional thermal expansion. And you can see low expansion or shrinkage along the horizontal direction after heating it by 70 Kelvin. By using spatially non-uniform arrangement of the microstructures, so we can also achieve thermally induced shearing, thermally induced rotation plus shearing, as well as thermally induced bending. And most of those behavior does not exist in natural material as well. And then by incorporating the origami design strategy, the metamaterials can effectively convert the thermal mismatch between two closely packed material into giant levels of biaxial thermal expansion or thermal shrinkage. So as you can see here, at large filling ratios of over 50%, these systems offer unprecedented negative and positive biaxial CTE from minus 6K ppm per Kelvin to 10K ppm per Kelvin. And these materials also show very large levels of biaxial thermal expansion, which is over 21% for 20 Kelvin temperature increase. And this is unachievable previously. So if you do a comparison of the current metamaterial design with the previous designs in this attribute plot, you can see our metamaterial design are marked here for the positive CTE versus the density. So the right graph shows the negative CTE versus the density, and our metamaterial design are denoted here. So from this comparison, you can see that our metamaterial design can substantially enlarge the accessible range of coefficient of thermal expansion. Excluding the microstructure design, the strategical utility of soft active materials can also provide an alternative route to active thermal expansion. Excuse me. In specific, we can introduce a mechanics-guided design and fabrication scheme of liquid crystal elastomer in the form of a 2D lattice pattern. And this design can enable a regular local liquid crystal alignment along the length direction after biaxially stretching the entire network. And this can allow access to unprecedented biaxial actuation capabilities. Okay, to achieve biocompatible actuation with the human body, we introduced a low temperature synthesis method of the LCE with optimized composition ratios. And this can allow a remarkable reduction of the pneumatic isotropic transition temperature to only around 45 degrees Celsius without evident loss of the actuation strain or actuation stress. And this video shows the reversible thermal shrinkage and the irreversible thermal shrinkage. So you can see a very large biaxial shrinkage after putting that into the hot water. Okay. And as you can see from these these two left images, the LCE lattice metamaterial and hydrogel both have comparable biaxial actuation stress and Young's modulus comparable to those of human skins. But the LCE lattice metamaterials show a much shorter activation time than the hydrogels. As you can see from the rightmost image, which are all based on the experimental measurements, our LCE lattices offer the largest value of elective biaxial CTE, which is around 33,000 ppm per Kelvin. And this value is more than 5 times larger than the values reported previously. Based on this developed fabrication themes, we presented a biocompatible breathable hemostatic patch, which consists of a layer of LCE metamaterial to offer tunable biaxial contraction when mounted on the skin, and also a dressing layer to provide simultaneously the chemical treatment. So this hemostatic patch can combine the treatment of physical contraction and chemical reaction. And in terms of the animal experiments, we considered both round and cross-shaped wounds in the SD rats, which correspond to tear and incised wounds. We treated the wounds with different strategies, including the dressing, suturing, patch without actuation, and patch with actuation. And this slide shows the results of animal experiments. For the round wound to recover with 80% wound closure, it takes around 6.8 days for the strategy with our shrinkable patch. And for the 2 control groups with the only dressing or with the patch without actuation, it takes around 10 days and around 9 days respectively. So our shrinkable patch can accelerate the wound closure. And since the developed hemostatic patch provides a rapid physical contraction only in the plane of the skin surface, it can also avoid the pressure-induced pathologies, such as the skin alcohol or the tissue necrosis, which could be possibly caused by the use of medical bondage. Okay, then I would like to make a short summary of this talk. In conclusion, we have incorporated strategically designed microstructures into the lattice network with the proper geometries and heterogeneous integration. The result, is a class of soft network designs that can achieve either biomimetic properties or unusual responses of swelling, thermal expansion, and Poisson's ratios. And these soft network materials can open up new application opportunities, such as the highly integrated stretchable electronic systems and shrinkable hemostatic patches for skin regeneration. And this work was done in collaboration with many superb research groups in the world. In particular, I would like to thank Professor Daning Fang from Beijing Institute of Technology, Professor Nguyen Huang, and Professor John Rogers at Northwestern University. Also, I would like to thank all the members of my research group. It is them who did all of those works. Additionally, I would like to deliver my thanks for the funding supports. And with that, I would like to close and thank you for your attention. Thank you.
Thank you very much, Professor Zhang, for a very inspiring talk. And it was wonderful to see one single material can, by structure design, have so many possibilities to manipulate, especially from theoretical point of view, if you can do a simulation before making the device or the structure, that opens up a wide scope for further pursuit. Now, my question is probably related. This network is soft and probably give a large deformation. So in the range of mechanical property, what kind of modulus, Young's modulus you're looking at? Is it in K or in M Pascal, or even harder? Can you tune that modulus along your design?
Yes, yes, very good question. Very good question. Actually, for our current study, we can use different kinds of constituent material to fabricate this network. And in our study, we focus on reproducing the mechanical responses of soft biological tissues. So in this case, the modulus is typically on the order of kPa. But actually, the mechanical response of the soft tissues is also nonlinear. So the tangential modulus of the tissues vary when you stretch it. It can increase by 10 times if you stretch it very hard. Through our network design, we can reproduce the entire range of mechanical responses of the soft tissues. Alternatively, if you use a harder material to fabricate the network, for example, in some of our previous study, we used metals to fabricate this network. And by doing so, we can achieve several hundreds of megapascals for the modulus of the network. So this actually depend both on the constituent material and also on the microstructure geometry of the network. So you can tune both parameters to design the modulus of the network material.